Hello and welcome back. Today we'll be doing question 5 from the 2022 MAT. This is a question involving doors. Let's get started. Alice is participating in a TV game show where n distinct items are placed behind n closed doors. The game proceeds as follows. Alice picks a door I, which is opened, and the item behind it is revealed. Then the door is shut again and the host secretly swaps the item behind door I with the item behind one of the neighbouring doors, I-1 or I+1. If Alice picks door 1, the host has to then swap the item with the one behind door 2. Similarly, if Alice picks door N, the host has to swap the item with the one behind door N-1. Alice then gets to pick any door again, and the process repeats for a certain fixed number of rounds. At the end of the game, Alice wins all the items that were revealed to her. So, as an example, suppose that Alice first chooses door 2. Then the diamond here behind door 2 would be swapped with either the apple here behind door 1 or the orange here behind door 3. Suppose that the host swaps the diamond with the apple. Then, if Alice chooses door 1, then Alice would just get the diamond again, and so she would walk away with the diamond. However, let's suppose that the host actually swapped the diamond with the orange. If Alice then chose door 1, then she would get the apple as well as the diamond from her earlier choice. Now that we understand how the question works, we can now move on to answering the question. Part 1. For n equals 13, give an increasing sequence of length 7 of distinct doors that Alice can pick that guarantees she wins 7 items. Part 2. For any n of the form 2k plus 1, give a strategy to pick an increasing sequence of k plus 1 distinct doors that Alice can use to guarantee that she wins k plus 1 items. Briefly justify your answer. For n equals 13, give a sequence of length 10 of doors that Alice can pick that guarantees she wins 10 items. For any n of the form 3k plus 1, give a strategy to pick a sequence of 2k plus 2 doors that Alice can use to guarantee that she wins 2k plus 2 items. Briefly justify your answer. Part 5. A. For n equals 3, give a sequence of length 3 of doors that Alice can pick that guarantees she wins all 3 items. Part B. For n equals 5, give a sequence of length 5 of doors that Alice can pick that guarantees she wins all 5 items. Part 6. For n equals 13, give a sequence of length 11 of doors that Alice can pick that guarantees she wins 11 items. Part 7. For any n of the form 4k plus 1, give a strategy to pick a sequence of 3k plus 2 doors that Alice can use to guarantee that she wins 3k plus 2 items. Briefly justify your answer. Part 8. For n equals 6, is there a sequence of any length of doors that Alice can choose that will guarantee that she wins all 6 items? Justify your answer. Pause the video to have a think, and once you're ready, restart to see if you were correct. Let's get started. So here, we can see that Alice should start to pick door 1. This, of course, will mean that the items 1 and 2 will be swapped. Now, Alice would probably like to pick door 1 again, because that would give a different item. However, as we are not allowed to choose the same door twice, we must move on to choose door 3. This could give 2 different results based on different swappings. However, we'll notice that from beyond item 5, nothing has been changed. Therefore, we should choose door 5. Continuing this pattern, we can see that choosing 1, 3, 5, 7, 11 and 13 will allow Alice to get 7 items. Now we'll move on to part 2. From the above, one can see that choosing all the odd numbered doors will allow Alice to get all of those items. As there are k plus 1 odd items in the first 2k plus 1 numbers, Alice can guarantee k plus 1 items out of 2k plus 1 doors. Now, of course, there is a better way of choosing doors. So, if we consider these two cases separately, then we'll see that if there are a group of 3 doors with doors to either side of them, then if you choose the central door twice, then you will be guaranteed to get 2 out of 3 of these items. Similarly, if we have 2 doors at the end with items on one side but no items on the other, then if we choose the end door twice, then we are guaranteed to get 2 items out of 2. This means that for 13 items, we can split the groups up into 2 and then groups of 3, and then one more group of 2 at the end. This, of course, is only possible with a number n of the form 3k plus 4, or 3k plus 1. In the case of 13, we'll see that this here gives us 10 total items. Notice now that the positions marked with arrows may be selected in any order, as the items cannot be swapped across these double lines. Now let's move on to part 4. For this, we'll use the exact same method. If we choose the end doors twice each, then we have 4 items already chosen, and 3k minus 3 equals 3 of k minus 1 unchosen doors. We can split these doors into k minus 1 groups of 3, and choose the middle door of each group twice, giving us 2 items per group. Combined with the 4 items we earned in the first step, this gives us 2 of k minus 1 plus 4 equals 2k plus 2 total items. Now for part 5. We can see that in part 5, if we choose 1, 1, 3, then we are guaranteed to get all 3 items, because choosing door 1 twice will give us 1 and 2. Choosing 3 will then give us the remaining item. Similarly, for B, if we choose 1, 1 and 5, 5, then we are guaranteed to get the items 1 and 2 and 5 and 4. Then we can choose item 3, which has not been moved yet. Now we'll move on to part 6. Notice that if we have 2 out of 2 or 2 out of 3 chosen items on the side of a group of 4 items, then we can split the group of 4 items into a group of 1 and a group of 3. If we choose the center of the group of 3 items first, then we can get 2 out of 3 of these 3 items. We can then, secondly, choose the singular item to get 1 out of 1 items for this group. In the case of 13 items, we can first split the ends off, and then split the remainder into alternating groups of 1 and 3. Notice, of course, that we can have a group of 1 over here without any loss. Now, if we choose all of the items indicated by the double arrows in the first row, first, in any order, and then all of the items in the second row in any order, then we can get a total of 11 items. Notice that we couldn't, for example, have chosen 1 twice, and then 3 before choosing 5 twice, because then the item 3 could have appeared in 4, and therefore we could have chosen 3 and 5 instead of 2 out of 4, 5 and 6. For question 7, we'll use the exact same method again. We'll first split off 2 groups of 2 at the ends, as we can guarantee 4 items from these. This leaves us with 4k minus 3 equals 4 of k minus 1 plus 1 doors. We can split these into alternating groups of 1 and 3, starting and ending with groups of 1. There will be k minus 1 groups of 3 and k groups of 1. We can now gain 2 items from each group of 3 for 2k minus 2 items, and then move on to gain 1 item from each single door remaining for another k items. In total, we'll have 4 plus 2k minus 2 plus k equals 3k plus 2 total items. Now let's move on to part 8. Firstly, we'll note that Alice cannot actually choose a sequence of doors to guarantee that she can have all 6 items. To show this, we'll only need to show that the host could prevent Alice from obtaining the last item. To do this, we'll have to assume that the host knows Alice's sequence, and I'll prove why that's okay later. So, Alice can first choose doors 1 and 6 twice each, leaving 3 and 4 unchosen. The host must then allow Alice to choose one of them, but can always swap or not swap the unchosen item away from Alice's next choice. We can assume the host knows Alice's list of doors, since a guarantee would obtain the same number of items regardless of whether the host knows or not. And that's our answer. If you liked our video, please like and subscribe, and we'll see you next time for some more fun maths problems. Thanks for watching, and goodbye.